Hey everybody, I have an interesting function today, and its graph. It's a function that's defined by a definite integral. Everybody remembers learning these in calculus, but you learn the formal properties, and I don't think in a lot of calculus classes they actually showed you the graph. But right here we actually have a function that shows the graph of the integral, where the integrand is this quantity t squared over the quantity t squared plus 3t plus 5. Now, important thing to understand about this, and it took me a while to get it, is what you see here, this integrand, t squared over t squared plus 3t plus 5, that's just the integrand. This is not the graph of that rational function. It's the graph of the interval point by point by point. And I struggle with that, but literally a point on the graph of this function has an x-coordinate that looks like this, and a y-coordinate that looks like what I've highlighted. Now, that's a complicated y-coordinate. Think if you had to do this by hand. Now, to get the point across, there's a nice natural interpretation of the x-intercept here. You can see that the x-intercept is 3, 0. It's cut there. You have 1, 2, 3. So there's the x-intercept of 3, 0. All right. Now, so let's scroll down to the next screen. Now you see what we've done here is we've actually defined the function. We called it g of x. And you'll see that this is the very same expression that you see kind of faintly highlighted right here, or this caption right here. And so g at 3, okay, you guys remember the properties of an integral. From 3 to 3, there's no area. You can think of it as a line which has no breadth, a line at a width of 0 if you want to. But so g at 3 as a function is easily no Riemann integrals, no Riemann sums required to do that. That area is equal to 0. So that kind of gets your footing here, 3, 0. Now, let's take a look. Now, just from the graph, without even thinking about this being the graph of an integral or of a definite integral, estimate phi comma y. Now, y, of course, would correspond to the value of this definite integral when x took on a value of 2. So if you go here and look just right above 5, it's looking like it's somewhere around 1, right? Just from the graph, without even thinking this is the graph of an integral. Okay, so we say right here estimate approximately 1 right here. So if you I actually had some computer software just do this. I didn't know if I could even integrate that, but it came out to be pretty close. It was actually right around 0.96, 0.96. So you see, this graph literally is the graph. Any point on this graph, a definite integral had to be computed. So a human doing this by hand, it would take ages to get even a close appearance. Now, I'm gonna talk about this a little bit more with respect to concavity. I'm just gonna go ahead and save that for another video. But one thing I would like to talk about before I let you go is, you see, notice this graph is always increasing, always increasing. And again, this isn't the graph of the integrand, because the integrand would pass through 0, 0, right? If you put 0 in for t. So this definitely is not the graph of that quotient as much as a lot of us want it to be. But notice this quotient, if you take the derivative of this by the fundamental theorem of calculus, the derivative of this integral equation is just the integrand. And this integrand is always positive. And you remember, a positive derivative corresponds to an increasing function. So that's another thing. And I was originally going to do the concavity piece, but I'm going to do that on the next video. Hope you guys enjoyed that.